So for this next session, which is going to be on space safety and sustainability, we're going to have a series of technical talks. The way this is going to work is that each presenter will go through their stuff. We'll save questions and answers for the end of the session.
Moriba, scooter.
Sorry. We'll basically save the questions till the end of the session, and that way we can bring in the questions from people that are attending online. So with that, our first presenter is going to be Benjamin Feuge-Miller. Yes, please go to the podium. No, I don't have that many graduate students. They don't last long with me, but Ben is the only one.
All right, that's good.
Try the other one.
Here we go.
All right. So now can you hear me?
Yeah.
All right. So we're going to begin by emphasizing the importance of having to make positional measurements of where objects are in space before we can do any kind of risk assessment or analysis about the orbital environment. And one of the tools we can use, which is most scalable, is to use optical sensors. Taking a telescope and pointing a camera at the sky and taking a lot of time series photographs of the orbitals of the space environment and trying to make detections of where satellites are in the same and use that to inform later orbital analyses. And on any kind of optical telescope frame, any actively tracked satellite our telescope mount is following will form kind of a Gaussian feature. On any kind of untracked feature such as star will be streaked across the image frame due to a finite exposure time of the camera sensor. And if we stack all a bunch of telescope image frames on top of one another and form a dense three-dimensional data cube structure, we can kind of assume that if we have low tracking noise, any actively tracked object may also form a streak-like feature in this kind of three-dimensional data cube. And
Hold on. I'm gonna advance it for you.
next slide.
There we go.
All right, so traditional methods of detection and tracking from optical telescope data have required that a priori we know exactly what kind of features we're looking for, and also that we are able to make strong characterizations of all the other possible noise sources in the data. And this means that these traditional detection pipelines require a large amount of calibration, which costs a lot of time and effort and expert knowledge of any particular detection pipeline in order to get them functioning to a strong degree. And we can use machine learning techniques to try to reduce the amount of a priori assumptions we make. But that requires that we take the time and effort to make a strong enough labeled training data set, which itself is a very challenging task to tackle. So we propose to instead come at this from a sort of new approach using a contrario principles, looking for any feature which is not attributable to any kind of surrounding noise, and saying that this kind of feature must be meaningful, and use this to try to identify our potential infiltrating space objects. So in the illustration that you have seen, the human eye is really well able to identify those features which are not attributable to chance. Your eye can make out an alignment really quite easy. This is practically going to be a hypothesis testing scheme. And we note that in any kind of data analysis, there's the aleatory uncertainty, which is the true statistical distributions of data, and there's epistemic uncertainty, which is our ignorance of these aleatory models. Now, traditional methods have assumed that we have really strong models of what noise is and what features we're looking for, and try to reduce epistemic uncertainty that way. Our approach instead is to reduce epistemic uncertainty in gradual layers, peeling away possible sources of data of noise until we're left with our potential space objects. And we have a sort of long gradual inference pipeline for applying this system using very, very simplified assumptions of possible noise sources rather than making any single high fidelity assumption of what we're expected to look at. And this allows us to learn information from the data without making any a priori characterizations. First, we tried to look for any kind of line-like or streak-like feature in our three-dimensional data cube, and then try to infer families of these streak-like features, including the common background star fields, hardware noise structures, and remove these from being considered potential anthropogenic space objects. And finally, out of some remaining noise, looking for the very limited number of potential anthropogenic space objects in the observed frame. And for this, we can also perform track association in such a nuanced manner, looking for alignments in the spatiotemporal data cube, which correspond to individual tracks of specific space objects. And as a quick qualitative kind of proof of concept of the implementation of this algorithm, we have used some data collected from the AstroNet telescope network operated by UT. And we're going to be using a observation of a Navstar 48 satellite in medium Earth orbit and a Starlink satellite in low Earth orbit, because these two scenarios have different tracking noises associated with them. The Starlink satellite being in low Earth orbit has a high relative velocity to the camera frame, and thus its motion is a lot more unpredictable in the camera frame. So on the slide before you, a bit convoluted, we have plotted the non-negligible pixel values in the time series to try to give you a sense of the three-dimensional structure of an optical time series. And you can make out these streak-like features, which are, most of them, the stars within the Navstar 48 observation time series. And we're able to detect both the actively tracked Navstar and an unidentified orbital object, which is streaking across the frame in such a manner that is not attributable to the sensor noise or some background star field without making any a priori assumptions of what their point spread functions look like. And in the medium Earth orbit case, we are able to make detections pretty well. In the low Earth orbit case, we do not perform as well, we don't have a strong precision because the higher tracking noise associated with the low Earth objects, because we are making strong assumptions of the, we are making linearity assumptions when we're doing this kind of streak detection and track association. We think that if we have a reduced population of possible features after we've moved most of the stars in the data, we can try to do a nonlinear track association and improve our precision in this application. But we believe that in the medium Earth orbit and higher Earth orbit observations, tracking noise is low enough that we can begin larger scale quantitative analyses of the performance of this algorithm as compared to traditional methods. And thank you for your time.
Thank you, Ben. Daniel.
All right. Hello, everyone. I'm Dan, and I am here from MIT's ARC Lab, and I am currently a PhD student under Professor Cislunar. Today, I'd like to talk to you a bit about the system-level risk assessment of the low Earth orbit environment that we're looking at. So the motivation is pretty obvious for all of us. I think we've talked a lot about how digital generation has been an issue and how there's just more and more stuff up there. And the chance of collision goes up as n squared, where n is the number of objects up there. So space traffic management policies and perhaps guidances and best practices will attempt to safely maximize this utilization of LEO. But we do need to have some high fidelity models to be able to see what the debris environment will look like. So we have some risk assessment when we try to put up more mega constellations and try to figure out what we can do from there. So there are a few ways to model collision risk in LEO. One is the probabilistic model. We can think about it as a Monte Carlo model. We have a propagation scheme. We're able to propagate all these orbits, sample the uncertainties, and put some probability density function. And as we all know, if we're trying to propagate tens of thousands, if not hundreds of thousands of objects, that is simply a very high computational cost. We're able to do this for the near future, and we do this for operational use. We're trying to figure out what might collide in the future, trying to have some conjunction assessment and maneuvers. But this is one of the traditional methods that we have used today. But we want to see what the degree models might look like in decades to come, centuries to come, and what that model might look like. So we are now also looking at evolutionary models. So models such as particles in a box. You might know it as predator-prey models, source-sink models. So we're simply looking at the populations that can interact with one another. And these dynamics are defined in ordinary differential equations that we'll go into a little bit. And this method, while we're not propagating each state of the objects, it'll be faster and better suited for long-term evolution. And there's a lot of literature in both of these methods, and you can see a lot more of it in the paper. But to give a quick visual example, you can see on the right what a propagation of uncertainty and velocity looks like. Here, the example is just for 500 meters per second difference in all directions. And you can see how in few orbits, you're already in a very different spot. So in a probabilistic model, for all those different spots, you'll be propagating all of those and trying to see in the future what the outcome looks like, where the objects are, have things collided with each other. But in the evolutionary model sense, we will only look at the population together, as you can see, because things are spreading out pretty quickly. So the evolutionary model, you can look at it in a few manners. We do have to define some populations that are going to be interacting with one another. Here we have a three population model from Jaycie that was published last year. It's a very simple model, just to give you a quick pointer of what it could look like. One is to define one as live satellites, another as direct derelict satellites, another as debris, and they can interact with one another in a very different manner. You can see down here, S dot, the rate at which S live sats increase. We have launch, which is a very big knob that we can turn, and PMD, post-mission disposal. I think we talk a lot about how to get rid of these debris. Are the satellites that are done with their lifetime able to come down, and other interactions that you can see. This is a very simple model, but we were even using that, we're able to look at the population dynamics from varying launch rates. So you can see here, if lambda, which is the launch rate per year, is 2,000, we'll just go to a simple steady state solution of some sort for all of these. But as soon as it goes up to something really high, you can see that, yes, we do increase our active satellites because that's what we're launching. But at a certain point, the debris population just goes up too high. This is pretty much what Kessler syndrome is. You can't put up enough satellites to keep maintaining that population. So we can also look at additional populations. I think we talked a lot about the untracked debris and lethal objects. These are scary because we don't know where they are. And I think Kevin mentioned earlier that debris pieces can collide with one another, and that is the most of the collisions that happen in space. And they can create even smaller debris that we might not be able to see anymore, and that still might be lethal. So how do you model those is something that we can look into. Now, I just want to quick point out that it's easy to keep adding different parameters and adding different populations. You can imagine population depending on the country of origin or the manufacturer. So these things might not matter much. So it's really important to keep in mind what populations we should model, try to keep things more interesting and more things that matter more. So in this case scenario, we do want to look at the untrackable lethal debris objects, because that is something that we do think is very important and something that will grow without being seen. So there is quite a bit of future work. I think we skipped this slide, but we want to examine the historical launch cadences and estimate future launches. And we have looked at the past, how many things are being launched, and you can see clearly that there is that peak at 550 kilometers in the past few years with Starlink. But we want to see where things are going, and we have all the FCC filings to see what the future debris population could look like. And we also want to have distributions for cross-sectional area, or ballistic coefficients, and nonlinear debris generation models to have a better understanding of what the debris evolution could look like. We also want to quantify this risk to be able to see if some, let's say an ASAT test happens. Let's say there's a collision that happens that we weren't expecting, or there is some sort of cascading effect, but it dies out prematurely. Like, what does that do to our environment and the relative risk compared to before? All right, that is it. Thank you very much.
Thank you. Perfecto.
Hello, thank you for having me. My name is Pablo Machuca. I am currently working with Professor Aaron Rosengren at UC San Diego, and we are working on the parameterization of Cislunar space for catalog maintenance. So the interest of this project lies on Cislunar space, which we are expecting it to be heavily populated or increasingly populated in the near future through large space projects like the Lunar Gateway. This may also involve small spacecraft being deployed in the Earth system. Now, this represents a challenge for the community because we will have a variety of orbits that will be populated, including distant retrograde orbits around the moon, periodic orbits around the Lagrange points, like halo or near rectilinear halo orbits. And we may also have transfers from or to the surface of the moon. The complexity of the dynamical environment poses a new challenge for the space domain awareness community. This is because we may have objects in orbits that are, unstable. We may have limited visibility windows, or we may also have perhaps spacecraft that have minimal station keeping. So then we will have a variety of orbits that are used, and the dynamics are complex in this way. So the aim of this project is to better characterize and parameterize the lunar trajectories of interest. And we are trying to link this to the implications for the space domain awareness community and for catalog maintenance of lunar space. Some of our objectives are to provide a more complete characterization of the orbits of interest, to propose and assess parameterization approaches that can intuitively represent the motion of these objects. We want to quantify uncertainties involved in the orbit determination process. Now we begin this analysis by reproducing in the 3D problem and in a ephemeris model some scenarios of interest. So, for instance, the first example that I will show here is a transfer between different orbits around the second Lagrange point, starting at the 922 resonant NRHO that is baseline for the Lunar Gateway. We transfer all the way to a smaller orbit in the vicinity of O2. So these transfers look kind of like this. We start at the 922 resonant NRHO close to the moon, and then we're using several halo orbits to go all the way to the Lagrange point. If we transition this into the ephemeris model, the plot looks a bit messier because now halo orbits are not perfectly periodic, they are quasi-periodic. But we see the same features transitioning from the NRHO to the smaller orbit around the Lagrange point. Now, once we're able to reproduce this kind of scenarios of interest, we are trying to look for parameterization approaches that are able to describe the motion of the spacecraft in a more intuitive way. So we are actually looking at orbital elements, that we are all familiar with. So we're using geocentric and selenocentric orbital elements depending on where we are in space. If we are within the moon's heliosphere, then we're using selenocentric orbital elements. We actually see that if we represent the states of the object relative to the synodic Earth-Moon reference frame, we are able to provide the most intuitive representation of orbital elements. This reference frame is just the one that has an x-axis pointing from the Earth to the Moon, and the y-axis is parallel to the relative velocity of the two bodies. Now, this plot looks very messy, but I'll try to explain it here. This is a representation of the semi-major axis along time for the three-body problem transfer. So in the x-axis, we have the time starting at the 922 NRHO, going all the way to a smaller orbit around the Lagrange point. In the left y-axis, we have the geocentric semi-major axis, plotted in black. And in the right y-axis, we have the selenocentric semi-major axis when we are within the moon's heliosphere. Here are some of the things that we observe. So we observe that orbital elements are actually well defined despite the non-capillarity of these orbits and the strong thermal perturbations. We actually see that orbital elements show a predictive behavior. They're actually periodic along their orbits. However, the oscillation of this orbital element representation changes depending on the orbit that we are on. And another feature that we observe is that maneuvers, actually impulsive maneuvers, result in sudden changes in the orbital element representation, and we are hoping to see that maybe this can be used for maneuver detection. If we do the same for the ephemeris model transfer, we actually observe that orbital elements are still well defined, and they show a similar behavior to that shown in the three-body problem. Now, however, because head orbits are not periodic anymore, so we see a quasi-periodic behavior in the orbital element representation as well. And actually, this is also seen throughout all the orbital elements that we use to represent. So here's an example for the eccentricity and the inclination in the problem. We see the same behavior. And if we do this in the ephemeris model, we see the same kind of trend, but now it's a Here just very quickly another example of another scenario of interest. Here is a transfer from a 922 NRXO to a distant retrograde orbit, and we are kind of observing the same Just as next steps for our project, we hope to further explore intuitive parameterization approaches to better characterize the motion of cislunar objects. We will introduce further scenarios of interest. We then will look into the quantification of uncertainties involving the OD process. And overall, what we want is to inform the space domain awareness community on viewing geometries and repair observation campaigns for cataloging of XU space. Just a quick mention that this work is supported by the Air Force Office of Scientific Research. And with that, I thank you very much for your attention. Please don't hesitate to contact myself or Professor Rosenberg if you have any questions. Thank you.
All right, Eashan.
Hello, everyone. So I am Eashan. I am an undergrad student at USC, and I'm a sophomore in the Air Force ROTC program. My research partner, Francisco, he's a senior, and then my research advisor, Dr. Michael Kazarian. He spoke earlier this morning, and we're going to be talking about identifying a cislunar and lunar orbit debris mitigation for the Artemis program. So first of all is for lunar exploration, what is our mitigation strategy for upcoming lunar missions, starting with the Artemis program? We know that beginning for LEO orbits, debris has been cluttering up for so long. And now if we don't provide good behaviors for cislunar and lunar orbits, that same cluttering of debris at LEO is going to happen for cislunar as well. So then that second question is, how do we prevent creating an orbital debris strategy for lunar and cislunar? So beginning our research, we started with the 18 Space Control Squadron, which is their role is to detect, track, and catalog space debris for any launches and for any launch getting from the US side. And they have not yet, but will develop methods for lunar and cislunar conjunction assessments. So their job is to catalog and track any kind of space debris going up, and then also providing risk assessments to any of their users that are planning to use SpaceTrack. So proposal for lunar and cislunar missions. Well, first of all, you can, if you're a space operator and you're using SpaceTrack's software or user agreement, they can notify users of potential collision assessments. And if you can perform a maneuver, then you can do the maneuver, that's good. But the problem is sometimes you cannot perform a maneuver. And so now operators have to send new trajectory files to the 18 Space Command to acquire launch approval. So what does this mean? If you're launching and you don't have the ability to avoid debris going through your paths, then you need to also show new data files so that there won't be any debris in your trajectory. Because if you cannot avoid any debris, then colliding into something is not a very good idea. So this is why we propose a pre-launch conjunction launch assessment. For example, in this picture, if you're going from a translunar injection orbit, so that's number 8 up there, to an outbound lunar orbit, which is around number 13. Once you're on that path, you can't really change your trajectory, right? So if there's debris at those points, such as at choke points, and you're not able to do a collision maneuver, that is very bad. So we want to have a process where before you launch, you show all your data files, and you show that before you launch, you won't actually leave any debris, and that you won't collide anything. So here are the challenges of lunar space situational awareness. On the graph on the right is potential launch windows for having simultaneous arrival of your landing ascent, your descent, and your transfer equipment for the lunar missions. The lunar windows to enter cislunar orbit are really small. So if you have any kind of debris, these windows are going to become closed. Right now, in the cislunar orbits, in lunar orbits, there's not a lot of debris, right? So there's a lot of windows. But if we don't change our behaviors, then these windows will become closed and we won't have a lot of opportunities. The second thing is a 4-day mission is really hard to propagate through data, right? The moon has a very irregular gravity. It has a really irregular moon gravity, and then also 3-body problems with sun and Earth perturbations make it really hard to model this. So you can't provide a very accurate risk assessment right now. And then this creates a derived requirement to precisely track potential outcomes. So if you can't really track debris very accurately for lunar system orbits, you can't really have a good accurate risk assessment because you have large covariance, then we shouldn't be launching yet until we can really do an accurate pre-cold launch conjunction assessment. Again, here are some challenges for the lunar conjunction assessment. Again, there is irregular lunar gravity field, we have solar radiation, and we have a 3-body problem. And then on the right is just showing a heat map of how irregular the moon's gravity is. And so if you have debris at unstable regions, even at choke points, they'll stay for long periods of time, which will reduce your launch windows that you want to have for those missions. And then a quick note is, again, cislunar transfer orbit is approximately 4 days. So error propagation over this time makes lunar collision assessments meaningless. So if you have any debris at those points that you don't know, that is not good. And then we need to also change those behaviors as well. So having a pre-launch conjunction assessment. Again, motivation for taking care of orbits. Here is a potential path to go to a lunar orbit. We're going to do the NASA program has to do a ballistic lunar transfer, which is much cheaper than going straight to the moon. But you can see at those points, there's TCM, which is a transfer collision maneuver. And at those specific points, or transfer course, at those specific points, if there's debris, then you can't really change your position very quickly. And so that's a problematic behavior. So you need to plan it out very carefully. And then this is just for simultaneous arrival for all equipment. So lastly, our recommendations. We need to have a zero tolerance policy for leaving. If you have a zero tolerance policy, then you would have good stewards acting up in lunar and system orbits. Lastly, you also need to have the sharing of SSA data to be mainstream. One problem we found out is when you're using space track software, you need to have a space situational awareness document to get any more emergency criteria. But some entities don't want to share that. Especially if you're doing government to government kind of sharing of data, they'll say ITAR, or they'll say specifically like, we can't share this data because it is proprietary. So that's not good. And here are my references.
Okay. Thank you. And next is Vishal.
Hi everyone, I'm Vishal. I'm a postdoc in C. Boulder. And today I'm going to present on our work on independent validation of Haskell densities that we are working with Kehan Space, Marcus here, and Ken Tabiska from Space Environment Analysis. provide context, what is HASTEM? So the Air Force High Accuracy Satellite Track model is really the gold standard for atmospheric densities right now. These are the most accurate density model that's out there, but it is not available to the commercial community or even the academic community. It's proprietary to Air Force. Now, HASTEM is a very important model when it comes to the protection of US space assets because it is really the density model that is used by the Air Force. Now, we propose a method that works in parallel to HASTEM to quantify the uncertainties around HASTEM densities. Even though HASTEM is a very accurate model, there are problems with it. The densities are available at a limited temporal and spatial resolution, and there are uncertainties in the space for the drivers that drive HASTEM. So we propose a model that works in parallel, which does not really change HASTEM, but which is able to quantify the uncertainties and provide a parallel stream of densities to HASTEM. Now, our method, the crux of our method is that we are proposing a simultaneous estimation of the density and the drag coefficient. Now, the drag force has the density and drag coefficient in a product factor, which makes it very difficult to observe them simultaneously. So any errors in the density will get absorbed in the drag coefficient, vice versa. So our method tries to decorrelate these two quantities. So in turn, basically giving a more unbiased density estimate. So this is the current operational calibration of HASTEM inputs. So we have calibration data from 80 to 90 calibration satellites, which are used by Air Force because they are kind of stable in terms of their attitude, so their ballistic coefficient is stable. These are used in conjunction with Space Environment Technologies S2K ops system, which really combines all the space for the drivers from different data sources and dynamically calibrates a baseline model, which many of you might know about. It's called JB 2008, and it's slightly modified for HASTEM called JB Eashan 9. So this is the current operational process for HASTEM. And the densities are really corrected at every 3 hours with a spherical harmonic coefficient kind of expansion. So our proposed validation in green works in parallel to this whole process. So we are not going to change HASTEM. It's a multi-million dollar process. We are not going to make changes to the whole process. But our process really combines data from different sources, specifically satellites that are carrying GPS receivers. So we are able to obtain tracking data at a very high frequency and where the attitude of the satellite is known. So we are estimating the drag coefficient by utilizing the time variations in the drag coefficient induced by the attitude of the satellite. So once we have a parallel stream of densities, we can use that to invert some of the uncertain space weather drivers that feed into HASTEM, specifically indices like F10. So this is a proposed method. We have our estimated states, and most important than that is the density and the drag coefficient that feeds into a dynamic model. And for a dynamical model, we are estimating corrections to our atmospheric density model, which is a baseline density model using stochastic correlated processes. And for drag coefficient, we are using a higher fidelity drag coefficient model, a Fourier drag coefficient model that our lab developed. So we feed it into an estimation scheme. We obtain our atmospheric density corrections and higher order time variations in the drag coefficient. The only problem with this method is how do we estimate the bias? Because the bias in density and drag coefficient is not observable simultaneously. So we invert some of the physical parameters that because drag coefficient is a dynamical parameter that really depends on the physics of your gas surface interactions. So once we have our higher order time corrections of drag coefficient, we can use that to invert the bias in the drag coefficient. And that really provides a more constrained model for the drag coefficient. And that can be then reused in our dynamical model to provide a more unbiased density estimate. So focusing more on that particular aspect, we have our initial estimates of our drag coefficient from a physical model. We obtain estimates of higher order time corrections. We invert that to obtain a more constrained physical model, and then finally get a better density estimate. So just to briefly go over this, we applied this method on a variety of simulations where we looked at different space weather conditions, different varying levels of solar and geomagnetic activity, and different altitudes as well. And we were able to constrain the density to an error of almost 10%. And finally, we applied this method to a precision orbit determination data from the Spire constellation. And Spire is a pretty good platform for us because it has frequent attitude maneuvers. And for this particular case, we take a time of low solar activity and low geomagnetic activity. So we estimate our densities using a baseline model like NRL-MSIS and GB2008. These are all state-of-the-art empirical models that are used by commercial operators right now. But as you can see, there are significant differences between these empirical models and Haston. And these translate to a huge error in orbit determination prediction. So yeah, so by estimating these corrections, we are able to improve our estimates by about 26% for 29% for MSIS and about 49% for GB2008. So we are able to obtain a better estimate of the densities by this method. So finally, in terms of conclusions, in the absence of other mismodeled errors, we are able to estimate the densities really well, and we show that by using real data from Spire satellites. Now, the main task that lies ahead of us is to quantify the errors in our estimated densities by looking at other mismodeled dynamics. What if your SRP, the solar radiation pressure, is not modeled properly? How does Earth radiation pressure affect the densities? And the last point is that like our method is a very generic method. It doesn't have to be used in parallel to Haston. It can also provide a parallel stream of densities that can be used to calibrate any semi-empirical density model that exists out there. And that's my last point. Thank you.
All right, well, hopefully we have everybody online. So with that, I have lots of questions, but I'm the moderator, so I'm not going to do that to people. From the audience, questions. Shall we start with Dr. Skinner? You want to?
Thank you. So I've got questions for each of you. I'll just ask them all, and you can then take turns responding. So Ben, you're up first. 3 questions. When you talk about celestial noise, do you mean like stray light, moon, that kind of thing, bright stars? Second question, when you talk about aleatory noise not being reducible, isn't it reducible by taking more measurements, like 1 over square root of n, that kind of thing? And the third question, have you considered doing a Galilean transformation to pull out those unknown tracks? We were doing that with some Woolly data, photon counting noise, photon counting data, and you could do a Galilean transformation to the coordinate system of the object that you don't know about. You could signal noise really zooms up. For Dan, I didn't understand your distinction between derelict objects and debris objects. It seems to me they're kind of the same. You could reduce the number of variables by just saying it's just that's what we just have to worry. And there's everything else. Pablo, there's an aerospace report some of my colleagues have worked on. I don't know if you guys have seen that. That could be very valuable to your work. Similar question to Eashan, that you might want to look at that Cislunar report that aerospace did. And also the question for you is, when you're doing Alcola, what's your probability, what thresholds for probability of collision are you recommending? 10 times 4, 10 times 5? What is your recommendation for that? That's a big area of discussion. And then for Ray, interesting talk. NASA, Kara, and aerospace have recognized the lack of a model that industry can easily use being something that's lacking. We're hoping that we're working with either Arcade or with the Department of Commerce Office of Space Commerce to bring in your industrial strength thing on. So I'd like to hear more about that.
Or how about you keep that for, yeah.
Yes.
Yeah. Try it on.
Now,
yeah.
Well, now. All right. So the first question was for the celestial noise. Yeah, we're interested in not trying to make any assumptions of what the star streaks are going to be looking like and where stars are located in the image, or try to do any or the classical reductions like reducing cosmic noise, and trying to account for any false positive projections might occur if lunar noise or other features are present in the data. The second question was about, sorry, I have to.
Auditory noise not being elusive.
Yeah, that comment was more of rather than making any kind of trying to average a lot of frames together or making assumptions of what exactly we're looking for. Try to infer structural information as opposed to, like, say, characterizing probabilistic PSFs of known objects. Or brightness distributions across the image, and try to infer these structures in the noise. And as for the third question, which was the gamma transfer or the transfers, we're going to be considering that next step of the research. This one is just an initial proof of concept, seeing if we could get an a contrarian method of making simple hypotheses about the data and trying to infer more and more information and see if we can use this to effectively make some kind of detection of space objects. Noting that we are making certain constraints, such as looking for linear features within the data, and noting that there are points in the inference, different steps in the inference framework where we can introduce these specific transforms in the next stage of research to improve the precision and accuracy of our estimates. Does that sound good?
All right, so the question was about derelict versus debris. So I'll give you the definition and then why it matters. The very beginning, we did just combine it as a payload versus debris, but then it didn't make sense to start adding it as a derelict satellite because the definition is it's a payload that hasn't been disposed of. So it's just an intact satellite that's just dead. It can't do maneuvers to avoid hitting other debris or. Yes, but when it hits a debris, it'll also generate a lot more objects.
Everything is, right?
Right, so the payload will as well on the derelict satellite as well too, but the fact is that the derelict satellites cannot, so there's a coefficient that changes how often it will be able to, for a payload, it's able to, let's say, do a avoidance maneuver, whereas a derelict would not. Not only that, payloads, if they're unable to do a PMD, post-mission disposal, then they'll become a derelict. So there is like a middle kind of purgatory kind of area where it's just satellite that's just dead and is unable to be removed by itself. That's, I think, the main distinction. And you're right, it is just a few coefficient differences, but it does seem to have some interesting dynamics. Yeah.
When was the Cislunar report released?
Came out within the last year. If you work with AFOSR, I'm not sure the release of it, but maybe have your major professor get in touch with us, sponsors.
So yeah, your question about calculating the probability, what that threshold should be. So US STARCOM, has the threshold being less than 5 kilometers, and then having it where the probability of collision would be 10 to the minus 6 or 10 to the minus 9. For me, I don't think that's a really good assessment. First of all, the space track doesn't tell you what the minimum distance is going to be between you and the object you could be colliding with, because they don't want to share their capabilities. Right? It's a government agency; they don't want to share too much information. But one question that was asked earlier to the panelists is, what happens when you have an operator-to-operator collision? Who's going to move? And I think if you want to share the cost of who's going to move, you need to increase that probability of collision to maybe 5% or 10%, significantly higher. I would assume that people understand that if there's a collision, then that's going to bring up lots of debris. But people don't want to expel their delta V when there's only going to be like 10 to the minus 6, right? So I think a proper threshold should be like 5% or 10%. And then you have to account for the covariance errors, right? Because the US STARCOM does all the covariance through ellipses, but there's a better way to do it using rectangular boxes where you can decrease the error maybe by 33 times, 5 times. But this US STARCOM doesn't do that because their database is so huge that would be computationally intense.
You want two mics? Is that what you want?
Yeah.
Go ahead.
Yeah, so I should have actually mentioned that this work is actually funded by an STTR grant with AFOSR. And so we are working with them to like have a product out there which basically provides a parallel stream of densities, ingesting data from multiple sources. Spire is one of them. Other commercial operators like Starlink could potentially be one of them. So if we have loads of data, we can actually provide these stream of densities that can be used to quantify the uncertainty in Sandstone. And on top of that, like I have been talking to folks from Code 61 who use Jang, who like work with the Jang software. And so like earlier there, the kind of philosophy they worked with was like, it doesn't really matter what the errors in your atmospheric model are because we are trying to do geodesy. So it doesn't matter. We can always absorb these errors in our empirical accelerations. But what about prediction? Because they are really concerned with geodesy. But we have managed to prove to them that if you have a better atmospheric density model, you still can reduce errors in your overall orbit simulation as well. And orbit prediction errors will also reduce. So we are trying to get these models out there with various folks in NASA and Air Force.
Well, so Air Force has their model, but there's a need for industry. So the open architecture data repository
Right.
to have access to that they can share internationally, which they can't with current.
That's true. That's true. Like Hasdem like it's not available to the commercial community. But these parallel stream of densities, they can be used to quantify the uncertainty of Hasdem, but they can also be ingested in the data assimilation framework for commercial operators. For example, the models that we use right now in our LMs in JB 2008, they have errors. But if we have other data sources that we can get from our method, like providing a parallel stream of densities, they can be used to improve models that are already out there. So this can, yeah. Oh yeah, that'd be great if we get more data from NOAA and SIPC as well.
Cool. We got a question up here. All right. No. I will fix it for you. Boom, 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 boom.
Thank you, sir. First, let me apologize in advance to the speakers because I forgot to start writing your names, and for the ones that I did write your names, autocorrect changed them, and so I'm not going to even try. Let me go then by number for the second speaker. Yes, sir. You had shown some simplified models that you used for your predictions and intend to do some future assessment based on those models. My question was, what have you done or what do you intend on doing in the future to validate the accuracy of those models based on historical data rather than trying to predict, just use historical data alone to validate?
Yes, that's a very good question. The model validation point is very important for sure, because we can just create our own coefficients and just run with it and just claim that this is going to cause cluster syndrome, and it's not going to, right? So there are all those listed, especially the Monte Carlo methods of NASA's Legend, ORDEM, and LISA's models that we're able to play around with. That will be our validation step, and that's how we will likely try to tune that. And of course, the future models, that's a little harder because it hasn't happened yet, but we do have the SSA filings and other proposed concepts, and we're able to compare that to other models that exist out there. And we just want to create something that is available for the community to use and be able to add on top of it in modular fashion, just other types of perturbations like space weather.
Thank you. For the third speaker, sorry, can you say your name one more time?
Pablo.
Pablo, you went over a chart that you called a scenario of interest. How do you define a scenario of interest near a libration point or Cislunar space?
So I guess we're basing the study on the lunar gateway and the different orbits that will be used to for that big project. So the lunar gateway is baseline to use a near rectilinear halo orbit. So that is part of most of our analysis. Then we have distant retrograde orbits that have been proposed as parking orbits for deep space missions. Then I guess it's part of the work. We're trying to see what the orbits of interest are based on what the community is doing.
So that's one of my origin, or the origin of my question rather, is there's a difference between what the community is doing to investigate future mission options that are, let's say, edging on, let's see if this is possible or that is possible, versus the practical from a spaceflight perspective. The specific scenario you showed that involved the transition between the different halo orbits. It's a very unique, often academic exercise, not really on the practical. But there are other practical scenarios to consider there. That's why I asked. The other question that I had for you was, when you were looking at the element representations, plots that had your oscillating behavior, and you had made a statement about them being well-defined. What do you consider as well-defined? And the reason I ask is because from my own trained eye and 20 years of experience working in that domain specifically, what I see is osculating behavior with increasing amplitude, right? Secular increase. And so elemental representations are not typically common in that domain. So how do you define that as being well-defined?
So to finish answering your previous question, the transfer between halo orbits that we were considering, actually the delta V for that is pretty high, so it may not be particularly practical, but it allows us to characterize the whole family of halo orbits. So that, that's I guess a positive point, even if it's not a realistic mission as such. About what was the second question? You remind me of the second question.
Yeah, the second question was what, why do you consider the parameterization as well?
Yeah, so that oscillating behavior that you observe is actually along different halo orbits, but each orbit itself has a bounded behavior. So in that sense, for instance, the NRHO close to the moon, it basically looks like a highly elliptical orbit around the moon. So it has a very bounded, very well-defined orbital elements. Now we actually saw that orbits that are closer to the Lagrange point have a very wide range of that oscillation. So in that particular case, maybe the orbital element representation is not particularly useful. Basically, we're just trying to see what happened. For some cases, it's actually useful. For the distant retrograde orbits, for instance, we see that it's also well-defined in the sense that it doesn't oscillate. The range of oscillation is not very big, so it still allows for an intuitive representation of the. Basically, if it tells us some relevant, it helps us to get familiarized with the orbit. Then I guess we're saying yes, this is helping us to get a more intuitive view. But and then we're trying to see what's the actual practicality of all of this, the real application.
Thank you. More question for the fourth speaker. So it's really not so much a question. I enjoyed your talk as well, but more of a comment that when we're looking at risk and in the cislunar and lunar vicinity, there are somewhat two categories to consider, in assessing risk. One is the things that we know for a fact are going to stay bounded in the lunar vicinity, and then there are the things that exist far away enough that are susceptible to the multi-body effects, and they pose perhaps a higher risk to things in Earth orbit because they can easily return and cross through the various Geo, Neo, Leo regimes in unpredictable ways, or rather chaotic ways. And so it's important, I think, for the community moving forward to pay attention to both in doing those simulations and finding metrics of risk assessment that are valid for those scenarios that fall in the chaotic part of the regime. So, but that was more of a comment. Thank you.
I definitely agree with that, because when we're studying the right ascension of the ascending node and the inclination angle, you get unstable and stable moments, and that degree can stay for a long period of time.
I think we have one more question and then we're gonna call it good. Here we go, Fred.
The question is for the first speaker. What was your name again?
Benji.
Ben. Okay. Could you comment on the knowledge, the priority knowledge that your system needs to detect an object? And the second question I have is, do you have some threshold in the signal to noise ratio? Capability?
The a priori assumptions making right now for the detection are that any feature of interest that we can detect must have some kind of linear streak-like feature in the dense data queue. So either it must be collected in either it must either be an unobserved object, the serendipitously passing through the frame, or we must be operating in a sidereal tracking mode so that there are the potential space objects form streak-like features. Or if we're actively tracking a satellite, we assume that there's low enough tracking noise that the Gaussian PSFs in the three-dimensional space are kind of conjoined into a coherent streak-like feature in the time domain. And then what was the second part of your question?
Signal to noise ratio threshold.
We haven't done a intense quantitative study enough to provide that. That's going to be the next stage of analysis. We were just interested in establishing a proof of concept that is effective detecting some kind of family of objects before moving on to the larger scale quantitative analysis. So that's going to be the next stage where we'd be interested in measuring the exact signal noise ratios, which can the detection.
Can you venture a guess? What level were you at?
I don't have the number off the top of my head for that. And we are interested in detecting not just the brightness of the signal, but rather we're operating in the gradient domain where we're looking just for coherent gradients of the streaks. So I don't feel comfortable and giving a specific number of the signal noise ratio just yet.
Thanks.
You know what? I don't know about you, but it sounds like we're done with this session. So round of applause for our speakers, please.